Kinesiology. Kinesiology, core training concepts. Chapter 6, Part 1. Core training concepts. Chapter 1, Part 1. Chapter 6, Part 1. Chapter 6, Part 1, Core Training Concepts. Chapter 6, Part 1, Core Training Concepts. Chapter 6, Part 1, Core Training Concepts. Learning objectives. Upon completion of this chapter, you will be able to explain the importance of the core musculature and its relationships to performance enhancement, differentiate the local stability, global stability, and movement systems of the core, describe the role of core training in improving sports performance and injury prevention. Describe the role of core training in improving sports performance and injury prevention. Identify the attributes of a systematic core training program for athletes at any level of training. Identify attributes of a systematic core training program for athletes at any level of training. Page 218. In recent years, sports performance professionals have increased the emphasis on core training in sports conditioning programs, as it has been shown that an efficient core allows for optimal acceleration, deceleration, and stabilization of the entire kinetic chain during functional movement. Kinetic chain: head, neck, lumbopelvic hip complex, knees, and feet. Historically, physical therapists prescribed core exercises for individuals with low back problems. Today, core training is a common practice for healthy athletes on sports teams and in sports conditioning centers. Core training concepts. Anatomy of the core. The neuromuscular skeletal core of the human movement system is defined by the structures that make up the lumbopelvic hip complex. So the core is the lumbopelvic hip complex. It's your hips. An efficient core ensures optimal length-tension relationships of functional agonists and antagonists, front and the back muscle, which makes it push and the pull muscle, which makes it possible for the human movement system to maintain favorable force-couple relationships throughout the lumbopelvic hip complex. Maintenance of optimum length force-couple relationships throughout the lumbopelvic hip complex. Maintenance of the optimal length tension and force-couple relationships allows for optimum joint arthrokinematics in the LPHC during functional movements. This provides ideal neuromuscular efficiency throughout the entire human movement system and allows the best possible acceleration, deceleration, and dynamic stabilization during integrated dynamic movements. The core operates as an integrated functional unit, enabling the entire lumbopelvic hip complex to work synergistically to produce force concentrically, decelerate force eccentrically, and stabilize against abnormal compression, stabilize against an abnormal compressive, torsional, and shear force and isometrically. Pro tip: by combining assessments with applications of core training, a target program can be developed to ensure peak performance is achieved along with preventing injuries. Pro tip: by combining assessments with applications of core training, a targeted program can be developed to ensure peak performance is achieved along with preventing injuries. So apply some core workouts and it will help you assess. In an efficient state, each structural component of the core distributes weight, absorbs force, and transfers ground reaction forces to maintain the athlete's center of mass over a constantly changing base of support. This neuromuscular efficiency of the core or lumbopelvic hip complex is often referred to as core stability, but is more accurately described as LPHC stability comprised of local or intersegmental stability, local stabilization system, global stabilization system, and global mobility and global stabilization system. This interdependent system needs to be appropriately trained to enable it to function efficiently during dynamic activities. Core stability definition: LPHC stability comprised of local or intersegmental stability, local stabilization system, global stability, global stabilization system, and global mobility. High-level sports performance requires functional strength, power, neuromuscular control, and muscular endurance in specific muscles. A well-designed integrated training program ensures the body stabilization system functions by using the developed strength, power, neuromuscular control, and muscular endurance of its prime movers. However, many athletes fail to develop the muscles required for optimal neuromuscular efficiency and stabilization of the LPHC. If the extremity muscles are strong, outer muscles, and the core is weak, core of your stomach, LPHC, there will be insufficient forces transferred throughout the human movement system for efficient movements. A weak core is a fundamental problem inherent to a weak core is a fundamental problem inherent to inefficient movement that may lead to predictable patterns of injury. A properly designed integrated core training program, however, helps an athlete gain neuromuscular control, stability, muscle endurance, strength, and power of the core. This integrated approach facilitates balanced muscular function of the entire human movement system. Greater neuromuscular control and stabilization provides a more biomechanically efficient position for the LPHC, allowing optimally sequenced activation, sequential kinematics, I guess everything firing correctly, and kinetics of the body segments that place extremities in the optimum position. So you have to get everything straight. At optimum velocity with optimum timing to produce the desired athletic task. Pro tip: basic athletic actions such as swimming, kicking, throwing, jumping, and sprinting require the trunk of the body to be stabilized while high amounts of power are generated through the core to the extremities. Stabilizing the core will increase the performance in such activities. Page 220. Functional anatomy. Functional anatomy. So part 1, page 220, chapter 6. Functional anatomy. To understand core training, the sports performance professional must fully understand functional anatomy, core, LPHC stabilization mechanisms, and normal force-couple relationships. A review of the key core musculature enables the sports performance professional to understand functional anatomy and develop an integrated training program. The core musculature has been divided into the local stabilization system, global stabilization system, and the movement system. To maintain core stability, integrated neuromuscular control of the local, global, and movement system is required. To maintain core stability, integrated neuromuscular control of the local, global, and movement system is required. So keeping a strong neural connection to your muscles in your core, really knowing how to fire them. Side note. Ensuring sequential coordinated activation of all systems at the right time with the right amount of force. The local core stabilizers are muscles that attach directly to the vertebra. These muscles are primarily type 1 muscle fibers with high density of muscle spindles. So type 1 have high density of muscle spindles. So they're very dense. There must be tons of muscle spindles. Okay? These muscles are primarily responsible for intervertebral and intersegmental stability, working to limit excess working to limit excessive, compressive, shear, and rotational forces between spinal segments. These muscles also aid in proprioception and postural control due to their high densities of muscle spindles. The primary muscles that make up the local stabilization system include the transverse abdominis, internal oblique, multifidus, pelvic floor musculature, and diaphragm. The primary muscles that make up the local stabilization system include the transverse abdominis, internal oblique, multifidus, pelvic floor musculature, and diaphragm. These muscles contribute to segmental spinal stability by increasing intra-abdominal pressure and generating tension in the thoracolumbar fascia, thus increasing spinal stiffness for improved intersegmental neuromuscular control. You gotta learn how to, we're getting there. Quick review, table 6, local stabilization system, transverse abdominis, local stabilization system, internal oblique, local stabilization system, lumbar multifidus, local stabilization system, pelvic floor muscles, local stabilization system, diaphragm, global. These are all global stabilization systems. Quadratus lumbarum, global. Psoas major, global. External oblique, global. Portions of the internal oblique, global. Rectus abdominis, global. Gluteus medius, global. Add all the adductors, and gracilis and pectinus, global. The global core stabilizers are muscles that attach from the pelvis to the spine. These muscles act to transfer loads between the upper extremity and lower extremity and provide stability between the pelvis and spine. These muscles provide stabilization and eccentric control of the core during functional movements. Eccentric, very important, not concentric. Eccentric. The primary muscles that make up the globalization system include globalization system, quadratus lumbarum, psoas major, external oblique, portions of the internal oblique, rectus abdominis, gluteus medius, and adductor complex. Repeated after. Movement system. The movement system includes muscles that attach the spine and or pelvis to the extremities. These muscles are primarily responsible for concentric force production and eccentric deceleration during dynamic activities. The primary muscles that make up the movement system include the latissimus dorsi, hip flexors, hamstrings, and quadriceps. Primary muscles that make up the movement system include the latissimus dorsi, hip flexors, hamstrings, and quadriceps. That's the movement system. All of these muscles provide dynamic stabilization and optimal neuromuscular control of the entire core, LPHC. They not only produce force concentrically, contractions, but also reduce force eccentrically. So this is concentric and eccentric. Concentric here. Ooh, eccentric here. They not only produce force concentric contractions, but also reduce force eccentric contractions and provide dynamic stabilization in all planes of movement during functional activities. In isolation, these muscles do not effectively achieve stabilization of the LPHC. It is their synergistic interdependent functioning that enhances stability and neuromuscular control. It is their synergistic interdependent functioning, so synergistic things working together, synergistically functioning, that enhances stability and neuromuscular control. So it is their synergistic interdependent functioning that enhances stability and neuromuscular control. So they're working together synergistically. All the little muscles work together. That enhances stability and neuromuscular control. Strong connection. Core stabilization mechanisms. The core is stabilized during functional movement by two primary systems, the thoracolumbar stabilization mechanism and the IAP stabilization mechanism. The TFL is a fascial network of non-contractile tissue that plays an essential role in the functional stability of the core. The TFL is divided into the posterior, anterior, and middle layers. Although the TLF, tensor thoracolumbar fascia, TLF, sorry. The TLF is a fascial network of non-contractile tissue that plays an essential role in the functional stability of the core. The TLF is divided into posterior, anterior, and middle layers. Although the TLF is non-contractile, it can be engaged dynamically because of contractile tissue that attaches to it. The muscles that attach to the TLF include deep erector spinae, multifidus, transverse abdominis, internal oblique, gluteus maximus, latissimus dorsi, and quadratus lumborum. The transverse abdominis and internal oblique are particularly important for the stabilization. The transverse abdominis and the internal oblique are particularly important for stabilization. They attach the middle layer of the TLF via the lateral raphe. Activation of both obliques create a traction and tension force on the TLF, thoracolumbar fascia, enhancing the regional intersegmental stability and decreasing transitional and rotational stress of the core. Pictures. Pictures are on 222. 223, chapter 6. The second stabilization mechanism involves the IAP mechanism. Increased IAP decreases compressive force in the core. The abdominal muscles contract against the viscera, pushing the viscera superiorly into the diaphragm and inferiorly into the pelvic floor. This increase in the IAP results in elevation of the diaphragm and contraction of the pelvic floor musculature, while also assisting in providing intersegmental stabilization to the core. Intra-abdominal pressure mechanism. Intra-abdominal pressure mechanism. The second is the intra-abdominal pressure mechanism. The intra-abdominal pressure mechanism decreases compressive forces in the core. The abdominal muscles contract against the viscera, pushing the viscera superiorly into the diaphragm and inferiorly into the pelvic floor. This increase in the IAP results in elevation of the diaphragm and contraction of the musculature, while also assisting in providing intersegmental stabilization to the core. Page 223, close that out.